So, my name is Khalid Shmal. I will talk in this presentation about debugging Linux, then debugging Android, and third debugging the unified extensible firmware interface UEFI. What you should configure and in the debugger, and what you can do with the debugger. So we will talk first about Linux. I just do the simple test, just have a running Linux target attached to the target, stop the system. In this case here, I find the program counter executing at the C address. It is typical kernel address, just load the symbols, load the kernel symbols, and then I can have the source code. I can show the stack frame. Can show some kernel variables. For example, here the Linux banner. So it is like debugging a bare metal application, but actually this is not enough to debug a Linux system because you don't only have the kernel. So you want only to debug, for example, kernel modules, which are dynamic objects, to debug in user space, debugging processes, threads, libraries, and this needs some configuration in the debugger. Then the kernel itself, the structures of the kernel, the data of the kernel contain a lot of useful information, and it will be good to have some windows to display the kernel resources, for example, the task list, the loaded kernel modules, the loaded libraries for a specific process, and for this you need the Linux, what you call a Linux awareness. It is a TRACE32 extension. So first, let's talk very shortly about memory management. I show here in a very simple way. We have on the left side the virtual memory, and on the right side the physical memory. You have your kernel, which is running, for example, virtually at starting from C and 7 zeros, and has a certain range, and it is then mapped to a physical range. For example, here starting from 0. And you have the range for kernel modules, which is typically from BF6 zeros to the start of the kernel. And you have the user space. The kernel range is only used by the kernel and is always mapped in the TLB. The kernel modules, two kernel modules does not use the same range, the same address range, but for user space it is a little bit different. So you have many processes running. For example, here process run when you have, for example, 3 pages loaded, and they are mapped to 3 pages on the physical memory, but this mapping is not in the TLB because it's not the current process. And you have a second process, for example, with 1 loaded memory page, and this memory page is mapped in the TLB, so it is the current process. So for user space, we have first one problem. So two processors can use the same virtual addresses. So we need to distinguish in the debugger between these different user addresses. For example, if you have the address 8974, you don't know if it belongs to process 1 and process 2. For this, we use in the debugger an additional identifier, what you call space ID. For Linux, the space ID is simply the PID of the main thread for an application. So if you have a single-threaded application, it is the PID of the process. If you have a multi-threaded application, all threads have the same space ID, which is the PID of the main thread. And for the kernel, you have the space ID. We use the space ID 0. You can enable this memory extension in the debugger with a command called system.option MMU spaces on. You can see, for example, here on the left side we are in the kernel, so we have the space ID 0, and on the right side we are executing a process, an application. So we are in the user space, and we are executing in the process with the PID 2F4. Symbols are always bind to a specific space ID, so you should always enable the address extension in the debugger before loading any symbols. Otherwise, you could have problems on the symbols. So you first load the symbols, and then you enable the address extension, so all your symbols that you have already loaded could be then bound to the space ID 0, which is maybe not correct. So this is the first thing. Then the core can access only virtual addresses which are mapped in the TLB, and the debugger accesses then memory through the core. So the debugger can only see virtual addresses that are mapped in the TLB. This is normally the kernel and the current process or some part of the current process. But the debugger can access physically more memory. So the debugger can physically access all the memory that is already loaded or that has been already accessed by the core. But the user is normally interested in virtual memory. So the symbols are bound to virtual addresses. The registers contain virtual addresses. What the debugger do is, if the address is accessible virtually, the debugger will do a virtual access. If it is not accessible virtually, the debugger will try to do the virtual to physical address translation and then access the address physically. And this is transparent for the user, but you need to do some settings to enable the debugger to do this. So this way, the user will have access to all the available memory. It is not important if it is in the TLB or not, and it will be transparent for the user. For this, you need to do some settings in the debugger. Normally, you have the TLB, which contains the current translations for the core, for the kernel and the current process, for example. You have a bigger table in the hardware, the hardware page table, which is a superset. So the TLB is a cache of the hardware page table, and the kernel itself holds a copy of the hardware page table with more information. So if what we call the kernel page table. And with mu.format, you specify the start address. First, the format of this kernel page table. This depends on the Linux version and on the configuration. For example, for ARM, you have 3 formats: Linux, which is the standard one, and if you have a swap table, it will be Linux swap if you are using 2.6 kernel, and Linux swap 3 if you are using 3.x kernel, because the format has been slightly changed with later version of 2.6. Then you need to tell the debugger about the base address of this kernel translation table, which is normally always a specific symbol called swapper underscore pg underscore dir. And you need then to set the address translation, the kernel translation, so the virtual start of the kernel, the virtual end of the kernel, and the physical start of the kernel. So the start address of the virtual start address of the kernel is configurable in the kernel configuration. It is normally this config page offset, and it's normally C and 7 zeros, 8 and 7 zeros, or 4 and 7 zeros. Then to get the physical address and the range, you can use you can open a window in the debugger, so you can dump the hardware page table starting from the virtual start address of the kernel, and then you will get here the physical start address, which is, for example, 8 and 7 zeros. And if you scroll down in this window until you have no translation, or the translation is no linear anymore, you get then the virtual end address of the kernel. Or you get this from, so you know that the kernel, how many memory the kernel is using, and on which address you have RAM physically, and then you also can get this information this way. But you can also use the debugger to have this information. For example, here we don't have a swap table, so we are using mu.format and then the standard format Linux, and then this start address of the kernel page table, which is the swapper underscore pg underscore dir, C and 7 zeros, which is the virtual start, and to DC7FFFFF mapped to 8 and 7 zeros physically. There is also a way, we have a new command where you can let the debugger automatically scan these settings, and it is then translation.autoscan.on. So if you enable this, the debugger will automatically scan these settings. Then you need to do 3 more settings for memory management. As already said, the symbols are always bound to specific space ID, but there are some symbols which are used by all space IDs. This is the kernel range and kernel modules. If you have, for example, a system call you are executing in the kernel on behalf of a specific process, so you have the space ID of the process. To always have the view of the symbols for our space IDs, you need to declare a common region, which is the range of the kernel modules plus the range of the kernel. So this is, for example, starting from BF 60 to the end of the address range. This way, the symbols that are in this range will be accessible for our space ID, will be viewed for all space IDs in the debugger windows. And then the process of finding the physical address, the virtual to physical address translation is called table walk. So the debugger walks through the tables, different page tables to find the physical address. This is disabled by default. You need to enable this with a translation.tablewalk on, and then enable the address translation in the debugger with translation.on. So without translation.on, all the other three other commands have no effect. Then you should load what you call a Linux awareness. A Linux or an awareness is an extension to the debugger. So the most of the Linux support, of the operating support, operating system support is not implemented in the executable of the debugger, but it is a separate file which has normally the extension .t32. We do this mainly for two reasons. First, we support a very wide range of our operating system. So this way the user can load the awareness for the operating system he is using, and then when changes, it will be easier to make changes to the extension, to the awareness, and have an update of the awareness if there is, for example, a new version of an operating system supporting some new functionality or having something different. This way, it will be easier to make changes to the awareness and not always to update the whole software. You will find this awareness under your TRACE32 installation or on the DVD under